Okay? So we have a nonlinear situation now. We have some function of x. I don't know what it is. It's just some random function of x. Okay? So y equals some function of x. It could be, for example, x squared plus 4. It could be some cubic function, some sine of x function, some exponential function. It's just now a nonlinear function of x. But I want to work out what my rate of change is. In other words, how quickly is my thing changing? How quickly is my money changing at any particular point in time? So I need to play on this idea of gradient. Okay, so remember, gradient is just change in y over change in x. I need to play on this idea. So let's suppose I want to work out the rate of change at that point there. So just some random value of x. Okay, some random value of x. Okay. Well, clearly, if that's x, what's my y value going to be if it's just some function of x? So if I stick x into my function, my y value is just going to be f of x. Okay? No dramas there. All right? So what I'm after, in fact, let me draw it in blue, is the gradient of this line here. Okay, the gradient of this line here. So that's my tangent line. That's what I want to find. However, by definition, how many times does my tangent touch the curve? How many?
2.
It's just 1. Okay? So a tangent line, by definition, has to touch the curve once and only once. It literally just means it just touches it, just skims past it. Right? In fact, have you ever heard of the word tangible in the English language? It literally means you can reach out and touch something. So that's where it comes from. So tangent just means touch. Okay? It doesn't cut through it at all, it just skims past it. Yeah?
So for graph like that, you have 2 tangents there?
Possibly. So, like that.
Yeah, and there's really another.
Yeah, so you're getting into a good question there. Does that come down and touch it? Sometimes it does, but in this case it doesn't. Okay. But anyway, this is a tangent. Okay. Now by definition, my tangent touches the curve once. So when I think about this, I'm thinking about a literal change in y. Now, do I have a change in y? Do I have a change in x? No, because for this thing to work, I need 2 points. So if you think with my linear equation, with my y equals 3x plus 4, that was fine, because I could find 2 points that lies on a line, and I could work out the gradient between them. But in this case, because I just have a tangent, I can't work out another point. Okay, because I don't have another point. Like this point over here doesn't lie on the curve. Okay, so I need to be a little bit more sneaky. So what I do is I choose a point that is really, really close to it. Really close to it. Okay, so I've just blown it up for the sake of illustration. But let's imagine it's like 0.1 away from the point which I'm after. Okay, so I'm kind of approximating it. So in fact, let's define this. Let's say that the distance between them is really small. Okay, so I'm just going to call the distance between them h. All right, could be 0.1, could be 0.01, could be 0.001. What can I do? What can I do to make sure that the red line matches the blue line?
I mean, each should be closer to 0.
Exactly. Just make that ridiculously small. Like instead of being 0.1 or 0.01, make it really, really small, so that it's basically 0. But it can't quite be 0, can it?
No.
Because if it is equal to 0, then I'm slap bang on that point. But I want to make it as small as I possibly can. Yeah? So, all I need to do is just reduce h. Now the idea of reducing a value so that it approaches something but never quite reaches it is called, does anybody know? It's called a limit. Okay? So a limit literally means you're making it as small as it possibly will make it, or you're approaching the value, but you're never quite reaching it. So in this case, I'm making h approach 0. So it's getting really, really small, it's approaching 0, but it never ever reaches it. All right? So literally what I'm doing is I'm saying do the same thing. So do the same thing as I did before, f of x plus h minus f of x divided by h, but this time make h really, really small so that it approaches 0. Now, I need to update my notation on the left-hand side to sort of illustrate this, right? So here, I'm using the capital letter D. So I'm using the capital letter D. All right. D, does anybody know why we call, sorry, it's not D at all, it's a Greek letter D. Does anybody know why we use D? Difference. Yeah, well, it's literally to do with difference, right? I'm literally looking at the difference between points. So difference in Y, difference in X. Okay, this means change. So this means a big change. I could also use the lowercase delta, so lowercase d in the Greek alphabet, to mean a small change. But what I'm talking about here is a change that is so small that it's basically zero. Okay? So in that case, I would call it an infinitesimal change. Infinitesimal. I think I'm spelling this right. Well, look, I've run out of letters. I've used the capital letter delta. I've used the lowercase delta. So the only thing left to do is to go into my own alphabet, the English alphabet. I'll just go for D. Okay, lowercase d. So using the same idea, I just update it. So I end up with, instead of delta y, I end up with dy. Instead of delta x, I end up with dx. Okay. So when you see this dy and this dx, by the way, we say this as dy by dx. Okay, we say this dy by dx. When you see this notation here, all it literally is talking about is gradient. Okay, it's literally talking about rate of change. That's all it's talking about. Okay. Has anybody seen this idea before? Yeah. This idea here is called first principles. Does anybody know who came up with it?
No.
Very famous guy, Isaac Newton. In fact, it's a bit unfair to say he came up with it as well. There was another guy called Leibniz, German guy. They derived this idea in the 1600s. Okay, I derived this idea in the 1600s. In fact, they came up with this idea completely independently of each other. Okay, if anybody knows anything about Newton, he wasn't a particularly nice man, and he especially didn't like other people coming along and stealing their ideas or stealing his ideas. So when Leibniz came up with exactly the same idea at exactly the same time, Newton was not happy. And so a lot of people credit Newton, but I think, hey, look, Leibniz may well have come up with this thing on his own, but let's give him some credit. So these two guys came up with this idea. But yeah, it's literally talking about, so differentiation is literally talking about the maths of change. The maths of change. And as you can imagine, there are a lot of things in life that change. Yeah? So being able to talk about the maths of change is a really, really important idea. So, what I will do is I will finish off there, but can I ask you before you go, on the differentiation tile, I have uploaded these lecture notes. Okay, so these are lecture notes which I put together. They're a bit gappy in some places, like I haven't had time to update the plots in some cases, but I think they are good enough to support what we are doing in class. So can I ask you to have a read through these, okay? By the way, there's a really good YouTube series by 3 Blue 1 Brown, which is called The Essence of Calculus. I strongly recommend you go away and have a watch of those videos, okay? So it sort of talks about everything we're doing here and it kind of talks you through things in your own time. Strongly recommend those.